Every single time you connect to Wi-Fi or just plug in an Ethernet cable, you're tapping into this hidden physical world. So today, we're going to pull back the curtain and uncover the blueprint that actually makes it all work. It really does feel like magic, right? You click a button and boom, you're online. But underneath that seamless experience, there's a whole physical world of signals and hardware and, well, carefully planned designs. So let's dig in and see how it all gets started. You see, every email you send, every video you stream, it all begins its journey as a simple signal. And to understand how that signal travels, network engineers use this sort of universal map. It's called the OSI model. And we're starting at the very bottom, right at the foundation, layer 1, the physical layer. Okay, so before we can even talk about how networks are arranged, we have to understand what they're built on. And we're talking about the raw, fundamental language of computers. What's so wild about this layer is that it has no idea what a file or an email even is. Seriously, it has only one job: to send and receive a stream of ones and zeros, the raw bits, across a wire or through the air or over a tiny strand of glass. That's it. So you can think of this layer like a translator. It's turning the digital ones and zeros from your computer into actual physical signals, whether that's a pulse of electricity, a flash of light, or a radio wave. It's the layer that defines the rules for the cables you use, the shape of the little plastic connectors, and even the speed limit for your data. Okay, so we've got our hardware, we've got our signals, but how do we arrange all those devices and cables in a way that actually makes sense? Well, that is where the blueprint comes in. Think of network topology as the literal architectural plan for your network. Are all the computers connected to one main line, or do they all connect to some central point? This layout is absolutely critical because it dramatically affects the network's performance, its reliability, and frankly, how difficult it is to manage. So we're going to look at 3 classic designs, and each one tells a story about the trade-offs you have to make between cost, simplicity, and reliability when you're building a network. All right, let's start with a classic matchup. This one really defined the early days of local networks, and it shows why most of the wired networks we use today are built the way they are. I want you to imagine a single main street, and every single house on that street is connected directly to it. All the traffic, doesn't matter where it's going, has to travel on that one street. That's the core idea of a bus network. It is a beautifully simple design, right? You've got one long backbone cable, the bus, and every single device on the network just taps right into it. Easy. But that simplicity hides a pretty major flaw. The benefit is obvious. It's cheap, and it's pretty easy to set up because you use way less cable. But just look at that first drawback. Because every device shares that one cable, if there's a break anywhere along that line, the entire network goes down. That single point of failure is its Achilles heel. So to solve the problems of the bus, network architects came up with a completely different plan. They thought, instead of one shared road, what if every house had its own private driveway that led to a central roundabout? And that is exactly what a star topology is. Every single computer has its very own dedicated cable connecting it back to a central device, like a switch. And this is by far the most common layout for wired networks today. I mean, your office, your home network, it's almost certainly set up this way. Now, the greatest strength of this design is reliability. If one computer's cable breaks, only that single computer loses its connection. Everyone else just keeps working. The trade-off, though, is that you need a lot more cable, and if that central switch fails, well, the whole network still goes down. It just moves that single point of failure to a more protected central location. But what if you need a network that absolutely, positively cannot fail? What if having a single point of failure just isn't an option? For that, we need the most robust and definitely the most complex blueprint of all. Welcome to the mesh network. In a full mesh setup, there are no single points of failure. Why? Because everything is connected to everything else. This incredible web of redundancy is what makes the backbone of the global internet so incredibly resilient. If one path goes down, data just says, okay, no problem, and finds another way to its destination. So this design really highlights the ultimate trade-off. On one hand, you get this unparalleled reliability, but on the other, the cost and the complexity are just enormous. I mean, imagine having to run a separate cable from your computer to every other computer in your office. It's just not practical for most local networks, but it's absolutely essential for the internet's core. All right, now that we understand the local blueprints, how do we connect networks across cities or countries or even the entire globe? Let's look at two technologies that solve this problem in very, very different ways. First up, satellite. When you literally can't run a cable, you can just beam the signal up into space. A signal travels from a ground station all the way up to a satellite orbiting 22,300 miles away, and then all the way back down to a customer in some remote location.
And right here, we see the core trade-off. The pro is unmatched coverage. You can get internet pretty much anywhere on Earth. The con? Physics. That 44,000-mile round trip, even moving at the speed of light, creates a noticeable delay. We call it latency. And it can be a real pain for real-time stuff like video calls or online gaming.
Next up is a technology that cleverly took something really old and made it new again. DSL was a huge breakthrough because it figured out how to send high-speed digital data over the plain old copper phone lines that were already wired into millions of homes. The huge advantage here was that the physical infrastructure was already in place, which made it relatively cheap and easy to roll out. The main drawback, though, is that the signal quality gets worse and worse over copper wire. So the farther your home is from the phone company's central office, the slower and less reliable your connection becomes. And that brings us to a final thought. Think about it. Even your Wi-Fi router has to plug into a physical cable somewhere. As we demand more speed, more data, more everything, these physical connections, that mesh of the internet's backbone, the star layout of a data center, they're not disappearing. If anything, they're becoming more critical than ever. Thanks for watching.